measurements, which are observed quantities with both a value and a unit. And in this video, we're going to take a closer look at the units and what we can use them for. One of the techniques that is really important in chemistry is called dimensional analysis. And the idea here is that we take a measurement and we're going to determine what the value is in a different set of units. And as simple as that concept is, it's incredibly powerful for solving problems. An example could be if you're 18 years old and you want to know how many hours old you are, then you can do dimensional analysis to find that answer. You would start with 18 years, and my recommendation when you're doing dimensional analysis is to start with the number where the unit is not a fraction. In this case, we would just start with the 18 years. And then you set up a fraction next to it, and the important thing is whatever unit you begin with is the unit that goes on the bottom of the fraction. And then on the top of the fraction, you're going to put another unit where you know the relationship between the two numbers. So for example, I'm going straight from years to days. Now you could think of this a different way, and you could have said, well, I know how many months there are in a year, so I'll use months. But then if you say, okay, well, how many days are in a month, that becomes a little bit more ambiguous because some months have 30 days, others have 31, then you have February. So it's simpler and cleaner to go from years to days directly. So sometimes you have to be aware that you're making decisions about what units to use, and your choice of units can make a difference in how easy the problem is to set up. So we have years on the bottom and days on the top. And what that accomplishes for us is it means that the years we started with and the years that are on the bottom of the fraction are going to cancel because anything divided by itself equals 1. Now we have days. So those are our current active units, if you think of it that way. And so in the next conversion, we're going to put days on the bottom of the fraction. And this is a way you can start chaining these conversion factors together. So if you're really not sure what the next step should be, take whatever units you currently have, which would be either your initial units or the units on top of the fraction, and put those same units on the bottom of the next one. That way they will cancel each other out. And then we know the relationship between days and hours, which are the units that we want to end up with. So now all we have to do is fill in the values. We know there are 365 days in 1 year, there are 24 hours in 1 day. And then you can find the numerical answer by multiplying 18 times 365 times 24, and then you would divide by the numbers on the bottom, which in this case are just 1. And you would get an answer of 1.6 times 10 to the 5th hours. So this is a relatively simple example, but it hallmarks all of the important features of doing dimensional analysis. Because we work with the metric system, it's important to know how to deal with metric prefixes in conversion factors. It's something that comes up a lot. Conversions between metric prefixes can be done 2 different ways, and my recommendation to you is to pick whichever way makes the most sense to you and then stick with it, because the trouble arises if you get these 2 different methods mixed up. One way to think about it is that there are lots of little things in one big thing. So if you think about like having lots of little, centimeters or whatever in one big object, it's like you have lots of those in one of these. The other way to think of it is that if you have a small thing, that's equal to a tiny slice of the big thing. And so whichever way you think of it is going to determine how you set up your fractions in the conversion factor. So if you think of it the first way, where you have lots of little things in one big thing, you have, for example, 1,000 milliliters in 1 liter. So whenever you have a conversion where you have milliliters on one part of the fraction and liters on the other, you'd always fill in 1 for the liter and 1,000 for the milliliter. And that's going to be true regardless of which side of the fraction the milliliters are on. They could be on the bottom of the fraction, and then you'd still have 1 liter is 1,000 milliliters. If you do it the other way, it's a similar idea, but the values you fill in are different. If you have milliliters to liters, then you would say that 1 milliliter is 10 to the minus third liters. So it just changes which unit gets the 1 and which one gets a different value. So this is what I mean when I say you want to pick one of these methods and stick with it, because you want to make sure that your 1 and your not 1 number are associated with the correct units. Here are a couple examples of doing metric conversions. The first one asks, how many micrograms are in 0.00043 grams? We'll start with the number where the unit is not a fraction, in this case, the number of grams. And then you would put grams on the bottom of the fraction and micrograms on the top. And this is where you need to have those conversions memorized for the metric system. I like to say that there are lots of little things in one big thing. So I would say that 1 gram is equal to 10 to the 6th micrograms. In this way, the grams will cancel. I'm left with micrograms, and when I multiply it out, I get an answer of 430 micrograms. The second problem asks how many centimeters are in 15 kilometers. And this is an example where you're going from one prefix to a different prefix. And when you're doing that, you want to go through the base unit. In this case, the base unit would be meters. So we're going to convert from 15 kilometers to how many meters that is, and then from meters to centimeters. So we start with our 15 kilometers. Because we start with kilometers, that's going to go on the bottom of the fraction. And we know how many meters are in a kilometer. So now the kilometers cancel, and our active unit is the meters. So we're going to put meters on the bottom of the next fraction and then relate it to our target unit. What we want is centimeters. So this way the meters cancel, and now our active unit is the centimeters. And then you can fill in the values. You know that 1 kilometer is 1,000 meters and 1 meter is 100 centimeters. And when you multiply that out, you get your answer of 1.5 times 10 to the 6th centimeters. One thing that can come up when you're doing dimensional analysis is that you need to go from a length unit, something like centimeters or meters, into an area, something like centimeters squared or meters squared. Or likewise, you might have a length and you need to go to a volume. So you have something like inches, but you need cubic inches. And when you do this, there is a technique that you can use where if you know the length conversions, you can transform those into either area conversions or volume conversions. And I'll show you exactly what I mean by that with a couple of examples. The first one is if I'm starting with 1 square centimeter and I want to know how many square inches that is. Well, I don't know a conversion between square centimeters and square inches, but I do know the conversion between centimeters and inches, which is that there are exactly 2.54 centimeters in 1 inch. Now that I have the linear relationship set up, I want to square everything inside the parentheses so that my units on the bottom of the fraction match the units that I started with, which in this case are square centimeters. 1 squared is simply 1, so I'm going to ignore that. If inches squared, 2.54 squared, and centimeters squared. And now my units match each other. So the centimeters squared will cancel, and I'm left with the units of inches squared. And then mathematically this works out to 0.4 square inches. Likewise, we can use a similar approach when we're dealing with volumes. So for example, if I am starting with 1 liter and I want to know how many cubic meters that is, the first thing I'm going to do is actually convert from liters to milliliters. And this may seem like an odd choice, but this is actually very intentional. Whenever you're going from a volume in terms of liters to a volume in terms of a cubed length, then this is a conversion that you're probably going to do. I'll show you why in the next step. We have 1,000 milliliters to 1 liter. And then here is the key step, because there are exactly 1 milliliters in 1 cubic centimeter. Those two units are identical to each other. And so this is the most important conversion when you're going from liter type volumes to a cubic length volume. Now I have my active unit would be in cubic centimeters because the liters would have canceled and the milliliters cancel. But what I want is cubic meters. And again, I don't know off the top of my head what the conversion is between cubic centimeters and cubic meters, but I do know that there are 100 centimeters in 1 meter. And now I can cube everything inside the parentheses so that my units here match the cubic centimeters. 1 cubed is 1, and I have meters cubed, 100 cubed, and centimeters cubed. And that works out to be 0.001 cubic meters. I'll do another example for you. This question asks, how many cubic inches are in 4 liters? I'll start with my 4.0 liters. And now once again, because I'm going from a volume in liter type units to something that's a cubic length, I'm going to use that transition of milliliters to cubic centimeters. So that means I need to convert from liters to milliliters. And I know which order to put them in the fraction because I want the liters to cancel. There are 1,000 milliliters and 1 liter. Now I'm going to put in the conversion that 1 milliliter is equal to 1 cubic centimeter. So now the milliliters have canceled. And then I can put in my conversion between centimeters and inches. Once again, in 1 inch, there are 2.54 centimeters. Now I have centimeters on the bottom, but I have cubic centimeters on the top. So that tells me I need to cube everything inside these parentheses. The inches get cubed, centimeters get cubed, and the 2.54 gets cubed. And again, technically the 1 does as well, but 1 cubed is simply 1. So now the cubic centimeters cancel out, and the unit that we're left with is cubic inches, which is what we want. So when you actually do that calculation, you end up with 244 cubic inches, which should only have 2 sig figs, so that actually rounds to 240 cubic inches, and that would be our final answer. Okay, imagine taking a road trip, right? So if it takes about 2.5 hours to drive from Mount Sac to San Diego Zoo, if gas costs $3.50 per gallon, and my car, for example, gets 39 miles to the gallon, the question is how much money does it cost in gas to take that one-way trip? You should get an answer of $11. One of the things you need to figure out with this problem is what number do you start with? Because there are a few different numbers here that you could. Now, the $3.50 to the gallon, the units there is dollars per gallon. That's a fraction, so you probably don't want to start with that number. 39 miles looks like it doesn't have a fractional unit, but it's miles to the gallon. And so that's really miles per gallon, which means that's also a fraction. So now you are going to have to decide between 121 miles and 2.5 hours. But if you look at the conversions, neither of the conversions you're given have anything to do with time. But we do know something about miles. So that means we can ignore the 2.5 hours and start with the 121 miles. And that's the thought process you want to go through when you're trying to figure out, where do I begin? Because beginning these problems is often like 80% of the work. If we start with 121 miles, then I know that we need to put miles on the bottom of the fraction. And then I go back up to the problem. I say, okay, well, what do I know that relates miles to something else? Well, I know how to relate miles to the gallon. And there are 39 miles per 1 gallon. Then in the next fraction, that means I'm going to put gallons on the bottom, and the unit I can relate it to would be money in this case, and that says it's $3.50 per 1 gallon. So now the miles have canceled, the gallons have canceled, and you're left with money, and that works out to be $11. Another thing that comes up with dimensional analysis a lot in chemistry is that oftentimes the quantity that you're trying to find will actually itself have units that are a fraction. And when that happens, you find your numerator and denominator separately, right? So you're finding the two components of your fraction separately, and then you divide them at the end. And so you may end up having to do dimensional analysis to find both the numerator and denominator in their own individual correct units, and then you can do that division. An example of this kind of quantity where the value you're looking for is itself a fraction is something called the mass density. Usually in chemistry, we just call it density. So if you just see the word density, this is what we mean. But the reality is there's actually lots of different kinds of density. So sometimes chemists are a little bit more specific and we say, oh, it's actually the mass density. But really those two terms are interchangeable. Density is defined as the mass of a substance divided by the volume that it occupies. And it's important to realize that this is for the same substance. So if you have a lump of some material, it is going to occupy a certain volume based on how much mass you have. Or you can think of it for a certain volume of the stuff you have, it's going to weigh a certain amount. And this is true for pretty much all materials. They all have their own inherent density. Water's density is really important. This comes up all the time, so this is a value you should have memorized. The density of water is 1.00 grams per cubic centimeter. So even though this is a number you have to memorize, as far as memorizations go, it's pretty straightforward. It's just 1. But the units are important. Grams per cubic centimeter. The grams is reflecting that we have a mass involved, and the cubic centimeters are reflecting the volume. You also sometimes see densities reported as grams per milliliter, and that's because a milliliter is identical to a cubic centimeter. I tend to prefer this cubic centimeter notation because it makes it less ambiguous with some other quantities that we'll learn about later in the semester. So the equation for density is that density itself is equal to the mass of the object divided by its volume. The mass should be in grams and the volume should be in cubic centimeters. And then when you do that division, you get the density in grams per cubic centimeter. So we can use this equation to either find the density, or if you know the density and know either the mass or the volume, you can use this equation to solve for the component you don't know. One of the uses for density is to tell us if an object will sink or float in a liquid, usually water. In this example, if we look at an apple, apples have a bit of a range of densities, but all of their densities are less than the density of water, and so they will float. But a potato's average density is greater than the density of water, and so potatoes will sink. I want you to think about this problem and pause the video while you're working on it. Once you have an answer, go ahead and unpause. But I want you to determine which of the following substances would have the largest density. For your answer, you should get number 3, a material that sinks in ethanol but floats on water. So let's go through the answer here. The material in number 1 has a mass of 10 grams and a volume of 2 liters. The first thing I would do is convert the 2 liters into cubic centimeters using the techniques that we've talked about. We know we would go from liters to milliliters. In 1 liter, we have 1,000 milliliters. And then from milliliters to cubic centimeters, which is 1 to 1. So that tells us that we have 2,000 cubic centimeters as our volume. And density is equal to mass divided by volume. So for number 1, that would be 10 grams divided by 2,000 cubic centimeters, which is equal to 0.005 grams per cubic centimeter. The material described in number 2 has a mass of 5 grams and a volume of 10 cubic centimeters. So if we do 5 grams divided by 10 cubic centimeters, this gives us a density of 0.5 grams per cubic centimeter. And then finally, to assess the third material, it sinks in ethanol but floats in water. The density of ethanol is 0.810 and the density of water is 1 gram per cubic centimeter, which means that the density of this material has to be somewhere between 0.81 and 1, which is a larger value than the other 2 densities. In this problem, you have a couple of ways that you can go about solving it. You can either use the density equation to solve for your missing piece, or you can use the density as a conversion factor. Whichever way you do it, you should get the same answer. So go ahead and work through this problem and then unpause when you're ready to see the answer. You should get an answer of 22.44 grams. I'm going to go through the answer using the density as a conversion factor. So I'll start with the 28.56 milliliters, and then I can convert from milliliters to cubic centimeters because that's a 1-to-1 ratio. In the next conversion factor, I would then put the cubic centimeters on the bottom of the fraction and grams on the top. So my milliliters will cancel and my cubic centimeters will cancel. If you put the units in first like this, then you don't have to stress about thinking if you should be dividing by the density or multiplying by the density, because it all works out with the units when you put those in. So you put in the values, you would say it's 0.7857 grams per 1 cubic centimeter. And so that way the cubic centimeters cancel and you're left with grams. And when you multiply it out, you get the 22.44 grams.